With Kroger brand products from Baker's, you can make all your favorite things this holiday season. Because Kroger brand's proven quality products come at exceptionally low prices. And with a money-back quality guarantee, every dish is sure to be a favorite.
These are a few of my favorite things.
Whether you shop delivery, pickup, or in-store, Kroger brand has all your favorite things. Baker's, fresh for everyone.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the first of the 2020 editions of the Space Nuts podcast. Thanks for sticking around. I know it's been a long wait, but we certainly do appreciate your support. Lots of emails and questions during the last few weeks while we've been resting it up. Fred's been sunning himself in the Arctic on his lilo or his deck chair or whatever it is you put on the ice. I have been watching cricket. Very much enjoying it. Australia winning 5 out of 5 tests. Yes, we had a great season. And I think last night they gave India a bit of a dust up too. I don't mind us beating India. Don't mind us beating everybody. Now, we've got a lot to get through, but we should welcome astronomer at large, Professor Fred Watson. Hello, Fred.
Hi, Andrew. I don't quite know how you'd get on with a lilo in the Arctic. And we saw the sun on, I think it was the 8th of January when we flew south from the Arctic Circle down towards Stockholm. We actually watched the sunrise from the aircraft. It was an amazing thing.
Wow, yeah, because you would have been way up where you couldn't see it at all. It would have been dark.
The sun didn't rise for most of the trip. It gets light. You see daylight. It's kind of twilight. It's actually really quite enchanting, but you don't see the sun. What we did see, though, and anybody who follows at Stargazer Fred, my Twitter feed, will see them. We saw a really rare phenomenon. We were there for the Northern Lights, the aurora, and we certainly saw a little bit of auroral activity. But the spectacular thing was some things called polar stratospheric clouds, which are very rare.
Wow.
And they are very colourful. And so these were clouds that are high enough in the atmosphere that even in the Arctic, where the sun does not rise, the clouds are still being lit by the sun because they're up to 25 kilometres above the surface.
So they're different from noctilucent clouds?
They are, yes. They are spectacularly different because they're full of colour. And the noctilucent clouds are basically just shimmer in a whitish colour, and you see them during the night, but which is why they're called noctilucent, night shining.
Oh.
Whereas polar stratospheric clouds are seen during the day and are brilliantly coloured. They were truly spectacular, quite breathtaking, Andrew, as you might guess from my enthusiasm.
Photos?
I'll send some photos.
Oh, yes. We'll send one to Hugh and he can pop it. I'll put it on our Facebook page. That'd be a good idea.
I'll be happy to do that.
Lovely. Oh, and Happy New Year, by the way.
Oh, yes, of course. There was a new year somewhere in the offing. Yes. A nice new round number.
Fred's resolution for 2020 is to discover a comet that's going to destroy Earth and get it named after him before it happens.
Yeah, you really wouldn't want to be the person who did that, would you?
No, I don't think so. That would be come famous. Oops. Yes.
It just gives you somebody to blame, doesn't it?
It does. It does indeed. Today we're going to talk about the oldest solid material ever discovered, which is an interesting find, older than us, older than our sun. It's a very old episode. We're going to look at an old star that's been identified and answers a question about the formation of our galaxy. And some questions from the audience about the relative frequency of stars based on the spectral scale. Thanks, Lauren. And Andrew asks about telescopes and weight. Can't do much about your weight, Andrew, but we might be able to answer questions about telescopes and much, much more on this edition episode 185, Fred, of the Space Nuts podcast. Now, to our first topic, the solid material, what appears to be the oldest solid material ever found on Earth, and it's older than Earth.
It is, that's right. Isn't that a conundrum?
It is a conundrum.
And the reason why, the way that conundrum is resolved is the fact that this thing was not found on Earth. This grain of solid material, it's stardust, was found inside a meteorite, which actually is one of the most perhaps productive scientifically meteorites that has ever been found. It's called the Murchison meteorite. It landed in the little town of Murchison in Victoria, which is a state of a state of Australia, not New South Wales. That's a different state. Murchison, a town in Victoria, one of the Australian states in the south of the country, back in 1969. So that meteorite it basically hurtled through the sky during the day. It was a Sunday morning. People were on their way to church. This thing flashed through the sky, and then people started finding bits of rock. And it turned out that these were bits of debris from a meteorite which has been very, very productive in terms of what it's taught us about the early solar system. So it's a particular type of meteorite called a carbonaceous chondrite, and they're the rarest. There are only about 5% of meteorites fall into that category. And it's full of organic material, compounds that are in some ways the precursors of life. Apparently, and this is something I didn't know, I read a very nice webpage produced by the ABC about the Murchison meteorite. It actually smells. The debris, really? It smells, and it's got, because it's full of carbon-related materials, organic materials, it's got a peculiar smell to it. Nobody's actually ventured to describe what it smells like. There was talk of there being a smell of methylated spirits when the thing came down through the atmosphere, but that could have been anything.
Yes, I suppose so.
Yeah. Anyway, coming back to the plot, among the contents of the Murchison meteorite are these grains of material which are literally stardust. They're the condensed grains of chemicals that were produced in a nebula far, far away because they don't belong to our solar system. How do we know that? Because they're much older than our solar system. So the sun and its family of planets are about 4.6 billion years old, but the grains of stardust that have been found within the Murchison meteorite range in age from that sort of number, but off to about 7 billion years. So the oldest ones are kind of nearly 3 billion years older than the solar system. That means that they have been formed in space by an earlier generation of stars than the sun, getting to the end of its life, sort of spewing off a nebula in which chemical reactions take place, and these little stardust grains form in that. And then that gas has formed part of the gas cloud from which the sun itself and its own planets were formed. And that's how it got, the grains got into the meteorite. It's a lovely story.
Yes.
Quite easy to find stuff on the web. Its composition, this is the 7 billion year old stardust. Its composition exactly matches what we see when we look with spectroscopic equipment at clouds of gas around old stars. And they name a couple, actually, the Egg Nebula, which is a nebula that looks like an egg. The Ring Nebula. I guess what the Ring Nebula looks like.
I'm not even going to say it out loud.
Yeah, it does. It looks like a ring. Very well known what are called planetary nebulae. It's the debris thrown off by a star when it gets to the last phase of its life. Our sun will do that in a few billion years' time. Put it in your diaries. So it's actually the ratio of carbon-12 to carbon-13, two isotopes of carbon in the dust grain, or the stardust grain, and it matches perfectly what has been found in this ring of gas in stars like the or nebulae like the Egg Nebula and the Ring Nebula. There's been some subtle methods used to date these stardust grains, but they're secure enough that people, the scientists who've done this work, are absolutely sure of themselves when they say that this one that is the oldest of them is 3 billion years older than the solar system. Great stuff.
Amazing. That's your explanation. Mine is that when you look at the compliance plate on the piece of stardust from the manufacturer, it's got the manufacturing date on it, and that's how we know that it's 3 billion years older than our solar system.
Yes, and that's... And, that's a lovely allegorical interpretation of what I just said.
And, of course, the other side to this story is that the humble town of Murchison has never done anything to cash in on the events of 1969. If you drive through Murchison, Victoria, you won't see aliens popping out. I'm lying. They have absolutely and utterly gone berserk on the thing.
Have they? Yeah, I've never been there.
Murchison's sort of become Australia's version of Roswell, I think.
Probably, yeah.
On a much smaller scale.
All it takes is one meteorite.
That's all it takes. Exactly right. Yes, but it is fascinating. It's good that they're still learning from that. That's fantastic. The scientists who've done this work say there's another 50 years worth of great research to come out of it. They're expecting to find grains of stardust that are even older than this as well. Oh, gosh. Fabulous. All right. We'll probably have more on that story in the future. This is the Space Nuts podcast. I'm Andrew Dunkley, and he's Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, if you would like to become a patron of the Space Nuts podcast, it's easy. You go to patreon.com/spacenuts and sign up for whatever amount you deem worthy. It's not an essential part of being a space nut, but it is an option for you if you would like to support the Space Nuts podcast. Patreon.com/spacenuts. There are various levels of membership, but as the patrons who've already signed up know, we are starting to build up bonus material on the Patreon website. And we'll be adding to that very, very soon. So keep an eye out if you're a patron. If you would like to become a patron, that's where you go. And thank you to everyone who's signed up as patrons of the Space Nuts podcast. Now, Fred, we're going to talk about a lonely, lonely star in a galaxy not far away.
Yeah, very nearby, in fact, the one that we belong to. Yeah, this is it's a nice story. Once again, it's a story with multi-facets, which, of course, is always good when you've got some astronomy. You can pull in different bits of astronomy to build a big picture. So the star you're talking about rejoices in the name of New Indy.
Oh, I like that.
And the Nu is not NEW, it's NU. It's the Greek letter Nu, which is kind of halfway through the Greek alphabet. And since Greek letters are only assigned to pretty bright stars because they were the ones that were being observed, in the dawn of the invention of the telescope. That tells you that this is a star that can be seen by the naked eye. It's not particularly bright. You kind of need to know where to look, but it is possible to see it with the unaided eye. Why is it New Indy and not New something else? Indy is the genitive format, is that right? I'm using the right term there. I think I am. Yeah, of the constellation Indus, the Indian. So, New Indy means new of Indus. It's like all stars are named with a Greek letter, and then all bright stars are named with a Greek letter, and then this genitive form of the. I think I'm using the wrong term there. I can't remember. So long since I've looked at this stuff.
It's jet lag again, Fred.
The constellation name.
Jet lag.
Yeah, it's jet lag. Yeah, gosh. Yeah, I know. Could do without that. Never mind.
They have to develop a pill for that, I reckon.
Yeah.
Somebody came up with a jet lag pill.
What you do is you use light because light is one that regulates your circadian rhythms. So if you can beam yourself with the right kind of light, that can reset your clocks, and you're off on a good thing. Anyway, that's a slightly off the story topic, but we can talk about that some other time. So what's special about New Indy? It's a star whose First of all, it's a very old star. We have been able, and not we personally, but scientists actually from a number of different institutions, including one here in Australia, the University of New South Wales. Scientists there have observed this star with a spacecraft called TESS. And you and I have talked about TESS before because it's the one that finds planets going around other stars by the fact that the planets dim the light of the star as it passes in front. So TESS is very good at making really sensitive measurements of the brightness of stars. Now, at the kind of level that TESS can detect, there are other things besides planets passing in front of stars that make them go dim. And one of them is that stars themselves have an intrinsic vibration. They ring a bit like a bell. Our sun does that. If I remember rightly, the sun's period of oscillation is about 5 minutes, something of that sort. Okay. This whole science is called asteroseismology, and it's about measuring starquakes. So you can learn a lot by looking at the way a star rings like a bell. And New Indy has the kind of vibrations that you only get from a star that is very old. And in fact, it turns out that you can use these vibrations to make a very accurate estimate of the age of a star. It's actually one of the most accurate ways of estimating the age of a star. And it comes out for New Indy at 11 billion years. That's its age. It's actually, I'm looking at the original paper here, 11.0 plus or minus 0.7 billion years. So there's a 700 million year uncertainty on that, but that is pretty damn good for something that's 11 billion years old. Yes. So the age of the star has been well established. However, this star has another attribute which singles it out as being unusual, and that is its motion, because it's moving in a way that suggests it was disturbed by a collision between our own galaxy and one of the dwarf galaxies that it has absorbed in order to build up its present size. And that the movement of New Indy suggests that it was disturbed by a small galaxy called Gaia Enceladus, that's its name, when it basically crashed into the young Milky Way. Now, that piece of information, so associating the motion of New Indy with the collision, essentially gives you a date for the collision. It was probably, well, it would have
February
been...
February the 30th, it would have been.
November 30th?
February.
Yeah.
February 30th.
February 30th.
That's what had happened.
Yeah, it was before. It was basically before the star was formed. Mm-hmm. There's other factors come into this as well, not just the motion of the star, but some aspects of its chemical composition that associate it with this collision with the Gaia Enceladus dwarf galaxy. And what that has done is allowed scientists to date the collision with the dwarf galaxy, because this star has been formed after that, probably in the aftermath of that collision. And so we now have a date probably of about 11.5 billion years ago for when this collision took place, because we know the age of the star. It's a very nice piece of work, linking one thing with another and determining something that would otherwise seem to be very hard to find out about.
Yes, indeed. Do we know, and I may have asked you this before, do we know how many galaxies make up our galaxy?
No, that's a really good question. It's something that's constantly being worked on, because all of these galaxies that were absorbed by our own essentially leave fossils in terms of the motions of stars within our own galaxy. So if you find a whole group of stars that have got a common motion, they're all moving the same way, but they're within our galaxy, what you can say is these probably are the remnant debris of a galaxy that was gobbled up by our own. So what's revolutionized our studies of this is the Gaia spacecraft, and that's why that galaxy is called Gaia Enceladus, because Gaia is a spacecraft which was launched probably about 5 years ago. I can't remember the details. It's a European Space Agency spacecraft, and it is very accurately measuring the positions and velocities of stars. And so we now have a catalogue of, I think it's something like 1.5 billion stars, which we know, whose motions we know well. And it's from that set of data that you can start picking out stars with a common motion and working out that this was, these stars belong to a distant galaxy. So I don't know what the total is at the moment. It's probably something like 15 or 20 that we know about, but there might very well be many more that made up, that went to make up the galaxy as we see it today.
Fascinating, and it's an ongoing process. I mean, this is just going to keep happening into the future, as we know.
It is.
But we just won't witness much of it because it takes so very long.
Yes, it's hard to know. Well, there's two collisions happening as we speak.
That's right. Yeah, we were talking
two
about that before.
Magellanic clouds, which are basically being ripped apart by our own galaxy. Yeah.
Yeah, it's fascinating. All right, so there it is. We've been able to identify the early formation process of our galaxy, and there's much more to learn through all the. I think it's just great, Fred, that we can learn this because we've got technology now that the Greeks didn't have. They basically had to look out there and work it out through theory and mathematics. But today we've got equipment that does some amazing stuff and just gives us so much more of an insight into what's out there. And because it just dredges up so many more questions too. But occasionally we get a very good answer like that one. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, if you would like a T-shirt, we have T-shirts. We have T-shirts coming out our ears. They have the Space Nuts logo on them. They are made in all sorts of colours, if you like, black and white. They are just sweet. You can get one just by going to the Space Nuts shop. It just sounds too weird. But bytes.com/spacenuts, that's BITESZ.com/spacenuts. That's where you can go to listen to the podcast, but you can also scroll down and look at all the bits and pieces there that are for sale, including a whole bunch of books by one Professor Fred Watson, I notice. But why not check it out? And while you're online, why not follow us on Facebook? You can follow us on Facebook, but also subscribe via YouTube. We're trying to get our numbers to 1,000. We're in a race with another podcast that I won't name because I don't want them to win. But we are absolutely beating them to a pulp at the moment. But we only need, Fred, 135 more subscribers to YouTube to hit the magic 1,000. While we were away, the numbers increased. I don't know what that says. But they really went hammer and tongs. I think the numbers went up like 150 while we were on our break.
I think that speaks volumes.
I think it does too. Dear. So anyway, that is an option if you would like to help us out. Whatever format you choose to listen to us, we are grateful. Now let's get into some questions. This one comes from Lauren Bitara. Hi, Lauren. Thanks for your question. Hello, Andrew. I've been trying to read astronomy articles when I have time, and I have a question. If you discuss our galaxy in a future podcast, I think we just did, I was wondering, what does our population of stars look like based on the spectral scale, or how many KMG, all star types, etc., or type stars are in our galaxy? Do we see more of one type of star, and is this because of the size of our supermassive black hole at the centre of the galaxy? Thank you, Lauren Bitara. Whoa, she's been reading up big. That's a nice question.
So the bottom line with this question, the heart of the question, is about what we call spectral classification, and that is a way of classifying stars that actually goes back to, before the beginning of the last century. It was the turn of the last century was when this work was being done. And actually the main scheme that we have was set up by a woman astronomer, Annie Jump Cannon, one of the great pioneers of what we call spectral classification. What she did was she looked at the spectrum, the rainbow spectrum of a whole lot of different stars, saw that they were different. They had different features in them, this barcode of information that tells us about the materials of stars. And she tried to classify them. She just looked at the spectrum, classified them in alphabetical order, A, B, C, D, E, F, G, etc. And it was only subsequently that people realized that actually these classifications are telling you something physical about the star. Most notably its temperature, and that Annie Jump Cannon, her simple alphabetical sequence was actually in the wrong order. And so it was very quickly realized, and I should know the dates for this, I think this is early in the 20th century, that actually the order is not A, B, C, D, E, F, G, H, I, J, K, etc. It is O, B, A, F, G, K, M.
Oh.
There are a number of others as well.
It doesn't matter because the process was created and then it was augmented to suit the reality.
To suit the reality, exactly. It's a really nice story. When I was a young astronomer, and I'm sure this is still true today when people learn these things, the mnemonic.
I hate to tell you, Fred, but no, it's not true. You're not still a young astronomer.
I know I'm not, but there are still such people around.
Yes, all right.
Yeah, the mnemonic that is always used is, so it's O, B, A, F, G, K, M. It is O, be a fine girl or guy, kiss me.
Oh, I didn't think astronomers could be romantic. How
well, they're not. They're just, anyway, they are, yes. Oh, that wasn't an offer to you, by the way.
I didn't read it that way.
No, good. I'm glad to hear that. I just wanted to put the disclaimer in there. Be a fine girl or guy, kiss me. That's order of temperature. So the O stars are the hottest. Their temperature is well over 30,000 degrees Kelvin. By the time you get to M stars, you're talking about temperatures 2,400 to 3,000 thereabouts.
Okay.
Much cooler stars. Our sun sits pretty well in the middle, about 5,000 degrees. Temperature, and it's a G star, so that's the spectral classification of our sun. So what Lauren's question was about was, given this classification, what is the percentage of such stars within our galaxy? And that's pretty well known. It's been very well studied, and the answer is a little bit surprising, I always think, when people ask me this question. So the rarest ones are the really hot stars, the O stars. So the fraction of stars that are O stars is 0.00003%.
Wow.
It's tiny.
There'd still be a lot of them, though.
Yeah, it's still a big number because there's 200 billion or however many 100 billion stars in the galaxy. But yeah, a tiny fraction are the O stars. And the B stars, which are the next classification, they're a bit cooler, 10 to 30,000 degrees, about 0.13%. So you're still looking at very small numbers.
And actually, what's the percentage of the G-class stars?
The G-class stars like our own, 7.6%.
Oh, is that all?
Yeah. So you would think they were very common. They're much more common than the others. In fact, if you add up all the earlier classes of stars, the O, B, A, F stars, they only get to half of what the G stars are in terms of percentage. So all the others together are about 3%, the G stars 7.6%. But then you get to the K and M classes, and these are dwarf stars, and they are cool. As I said, their temperature's down to about 2,400 degrees, and they are by far the most numerous. So the K stars are 12.1%, and they're round about 3,000 to 4,000 degrees. The M stars, 2,000 to 3,000 degrees, 76.4%.
Whoa.
So they are by far the most numerous stars in the galaxy.
And the most annoying.
By a long way, they are annoying. Yeah, they're dwarf stars. We talk about them a lot, actually, when we talk about extrasolar planets, because many of the planets going around other stars have been discovered around dwarf stars, M stars. Partly because these stars are so common, but also because it's actually easier to discover planets around these dwarf stars as well.
Okay, interesting.
So, Lauren's, the final bit of Lauren's question. So she says, do we see more of one type of star? And the answer is yes, overwhelmingly. It's the M stars, the dwarfs, the cool dwarfs. And is it because of the size of our supermassive black hole at the center of the galaxy? Not really. That supermassive black hole, while it's sort of related to the size of the galaxy as a whole, remember it's about 4.1 million times the mass of the sun, it doesn't really sift the stars themselves. You know, the stars, the commonest stars are the dwarf stars, and that's the way it is no matter how big the supermassive black hole is.
Okay, fair enough. Understood.
Fair enough.
Very good question. Thank you, Lauren. It prompts a question in my mind, though. Is it possible that there may be more types of stars out there that we haven't spotted yet?
Yes. In fact, that is true. And particularly at the low end, the cooler end of that sequence. So we've talked about M stars. There are R stars and N stars and carbon stars, all of which are different varieties of these really cool stars. But then when you go cooler still, you get to this family of weird objects called brown dwarfs, which are somewhere between a planet and a star. So there's this continuous run from, you know, the giant hot O stars, 30,000 degrees, down to the coolest things, which are really just a hot planet. Yeah. We think we've got all bases covered, but there might still be unusual types of stars that we haven't really discovered yet, probably with unusual chemistry.
Okay. Very good. Thanks, Lauren. Let's move on to a question from Andrew Mortimer. Andrew's questioned us before. Hi, Andrew and Fred. An important question. Does Australia have enough telescopes? And he goes on to talk about different types. And should we still get a gravitational wave detector? Maybe the Space Nuts Club should fund one. I'll pay for half.
Good on him.
Good. And bonus question, since energy and mass are equivalent, how many electron volts does it take to equal 1 kilogram of weight? We'll get to that in a moment. So do we have enough telescopes in Australia?
Well, you're asking an astronomer, and the answer is you can never have enough telescopes. Doesn't matter where you are. If you'd asked
me to answer that on behalf of you, I would have said that.
Yeah. But we're doing pretty well, I have to say, particularly in the era in which we live today, where we are actually going to be hosting half of the Square Kilometre Array. The Square Kilometre Array, that giant radio telescope that's being built both in Western Australia and in South Africa. So one of the world's flagship projects, an international consortium, an international project, and we are playing a role in it. The visible light community, the visible spectrum and infrared, we are also doing very well because we now have this 10-year strategic partnership brokered by the Australian government with the European Southern Observatory. So that's going really well. It gives Australian astronomers access to the 4 best 8-metre class telescopes in the world. Should we still get a gravitational wave detector? That would be wonderful, but they are very, very expensive. And at the moment, there's no plans for that. Although I have to say, there is a strong gravitational wave community in the University of Western Australia. They did some of the pioneering work on this stuff 20, 30 years ago, and actually contributed to the technology that built the LIGO, the Large Interferometric Gravitational Wave Observatory in the USA. So we've played our part in that, but we don't have a detector on Australian soil. Maybe one day we will. But
if Fred cashes in his Maserati, perhaps, but no.
Yeah, but my Maserati is only a dinky toy, as you know.
It's still in its box.
Still in its box, yeah. So it's worth at least $20.
I know. It's gained value. Okay, so we're doing rather well in terms of telescopes, but yes, as an astronomer, we could always use more. Now, the bonus question, since energy and mass are equivalent, how many electron volts does it take to equal 1 kilogram of weight?
Well, this is going to be the shortest answer I've ever given because I can answer it with one number. And that number is 5.60958835718, times 10 to the minus 35. 10 to the plus 35. Sorry.
Did you write that down, Andrew?
How many electron? Well, let me summarize the answer. How many electron volts in a kilogram? 5.6 times 10 to the 35. That's the number.
Easy. That's all we really need to say, because that's an adequate answer, Fred.
Yep. It is both sufficient and necessary. Is that right?
Absolutely. All right. Andrew, thank you so much for your question. Thank you to everybody who's contributed. Don't forget, if you want some bonus material, it's available on patreon.com/spacenuts. Fred, thanks as always. Great to be back.
Yeah, it is good to be back, and we'll talk again very soon.
We will indeed. Professor Fred Watson, astronomer at large, and from me, Andrew Dunkley. Thanks again. We'll catch you next week on another edition of the Space Nuts Podcast.
Space Nuts.
You've been listening to the Space Nuts Podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.